Module 7, Section 5.2, Systems of Linear Inequalities in Two Variables. Objectives. Objective 1, solve systems of linear inequalities graphically. Objective 2, identify bounded and unbounded regions. Objective 3, solve applications involving systems of linear inequalities. Objective 1, solving systems of linear inequalities graphically. Let's consider systems of linear inequalities such as x plus y greater than 6, 2x minus y greater than 0. So taken together, this is a linear system of inequalities. We wish to solve such systems graphically, that is to find the graph of all ordered pairs of real numbers xy that simultaneously satisfy all the inequalities in the system. The graph is called the solution region of the system, or also called the feasible region. To find the solution region, we graph each inequality in the system and then take the intersection of all their graphs. Here is an example. Graph the system of inequalities y less than negative 1 by 2x plus 2 and x minus 4 less than or equal to y. These are the steps. Step 1. Graph each inequality of the system in the same coordinate plane. And step 2. The solution is the intersection of all the half planes determined by the inequalities in the system. So we need to shade the common region. The graph of the first inequality y less than negative 1 by 2x plus 2 consists of the region shaded in yellow. It lies below the dotted line y equal to negative 1 by 2x plus 2. The graph of the second inequality is the region shaded blue and lies above the solid line x minus 4 equal to y. The graph is the region which is colored both blue and yellow. Notice that the origin satisfies both the inequalities. So the shading side will be the side of the origin, and the common region is this up here. Corner points. A corner point of a solution region is a point in the solution region that is the intersection of two boundary lines. In the previous example, the solution region had a corner point of 4, 0 because that was the intersection of the lines y equal to negative 1 by 2x plus 2 and y equal to x minus 4. We can get this corner point easily by using a graphing calculator. If we graph these two functions, y1 equals negative 1 by 2x plus 2 and y2 equals x minus 4, graph these two functions and use the intersection key. Objective 2, bounded and unbounded solution regions. A solution region of a system of linear inequalities is bounded if it can be enclosed within a circle. If the solution region of a system of linear inequalities cannot be enclosed within any large circle, it is called unbounded. The first shaded region here is a bounded region because we can actually enclose this shaded region within a circle like this. The second region here is unbounded because if we try to enclose within any circle, we still have shaded region that goes outside the circle. Next example, graph the solution of the following system. Indicate if the solution region is bounded or unbounded. X minus 4y greater than or equal to negative 12, 3x plus y less than or equal to 4. So we have the two boundary lines here, 3x plus y equal to 4 and x minus 4y equal to negative 12. And if I substitute the origin coordinates, both the inequalities are satisfied. 0 minus 4 times 0 is greater than or equal to negative 12, which is true. Again, 3 times 0 plus 0 is less than or equal to 4. That is also satisfied. The first inequality has its solution shaded by the yellow, and the second inequality has its solution shaded by blue. So the overlapping region is the solution of the system of inequalities, which is this region up here. Example: solve the system graphically and indicate whether the solution region is bounded or unbounded, and also find the coordinates of each corner point. We have the inequalities 2x plus y less than or equal to 8, x plus 2y less than or equal to 8, and we also have the two conditions x greater than or equal to 0, y greater than or equal to 0. We are going to graph the two boundary lines and shade the common region that comes in the first quadrant. So we only need to shade the first quadrant region because of these two conditions. So this is what we are going to get, and this region is obviously bounded because I can enclose this within a large enough circle. To calculate the corner points, I need to take the boundary lines in pairs and solve for the intersection. So if I graph these two functions, y1 equal to 8 minus 2x and y2 equals 8 minus x divided by 2, and use the calculator, I can compute the intersection point to be 8 by 3, 8 by 3, which is this intersection here, labeled as B. So the coordinates of B are 8 by 3, 8 by 3. Obviously, origin is one of the corner points which has got coordinates 0, 0. The coordinates of C is calculated as the x-intercept of the line 2x plus y equal to 8. If I substitute y equal to 0, I will get 2x plus 0 equal to 8. So x will be 4. So this corner point will have coordinates 4, 0. Now to calculate this corner point A, interpret it as the y-intercept of the line x plus 2y equal to 8. So I can substitute x equal to 0. If I substitute x equal to 0, that equation will be 0 plus 2y equal to 8. So y will be equal to 4. So the coordinates of A is calculated as 0, 4. These are the four corner points. Graph of more than two linear inequalities. To graph more than two linear inequalities, the same procedure is used. That is, graph each inequality separately. The graph of the system of linear inequalities is the intersection of the graphs of the individual inequalities. So we shade the common region. Here is an example. We have three inequalities here: 8x plus 8y less than or equal to 160, 4x plus 12y less than or equal to 180, and x is less than or equal to 15. Also we are getting the non-negativity conditions x, y both greater than or equal to 0. When we graph these inequalities, the common region is indicated as the region shaded yellow here. Objective 3, application problem. Suppose a manufacturer makes two types of skis, a trick ski and a slalom ski. Suppose each trick ski requires 8 hours of design work and 4 hours of finishing. Each slalom ski requires 8 hours of design and 12 hours of finishing. Furthermore, the total number of hours allocated for design work is 160 and the total available hours for finishing work is 180 hours. Finally, the number of trick skis produced must be less than or equal to 15. How many trick skis and how many slalom skis can be made under these conditions? How many possible answers are there? Construct a set of linear inequalities that can be used for this problem. And then finally find the corner points. Here is a solution. We take two variables, x to represent the number of trick skis and y to represent the number of slalom skis. Then immediately we can write that x and y must be both positive because we cannot make negative number of skis. So these two conditions comes automatic. Now in the problem it describes that the number of trick skis has to be less than or equal to 15. So that condition will be translated as x, which is the number of trick skis, less than or equal to 15. So we will get this constraint here, that inequality there. That is one of the conditions. So in terms of the total number of design hours, we have a restriction that it cannot exceed 160. If we calculate the total number of design hours by multiplying 8 and x, 8 is the number of design hours for each one of the trick skis, plus 8 times y, where 8 is again the number of design hours for slalom skis, we will get the total number of design hours, 8x plus 8y, and this number cannot exceed 160 according to the problem. So that is why we get this second inequality here, 8x plus 8y less than or equal to 160. So that is a constraint on the total number of design hours. Then in terms of the total number of finishing hours, we only have 180 that we can use. So if we calculate the number of finishing hours, it will be, again reading the problem, 4 hours of finishing on each one of the trick skis. So it will be 4 times x total, and 12 hours of finishing time on each one of the slalom skis. So it will be 12 times y. So if you add them together, we'll get the total number of finishing hours. So this has to be less than or equal to the maximum available, which is 180. So that gives the next constraint here, constraint on the number of finishing hours. So this system of linear inequalities describes our problem mathematically. To solve this problem, we notice that the origin satisfies all the inequalities. So for each of the lines, we use the side that includes the origin as the shading side. And because of these two conditions, we will only be getting the shading within the first quadrant. So the feasible region is shaded in yellow. And notice that this is a bounded region and it has got 5 corner points. One at the origin with coordinates 0, 0. Then we have one up here. And this is a point on the x-axis, so it will be having coordinates intersecting with the vertical line. So it will be 15 for x, 0 for y. So that is this point up here. Then we have another corner point which is on the y-axis, and that is the y-intercept of the line 4x plus 12y equal to 180. So if I substitute x equal to 0, I will get the y value. So 4 times 0 plus 12 times y equal to 180. So if I solve for y, I will get y equal to 15. So that will be the point 0, 15. Now we have 2 more corner points here. One up here, that will be on the vertical line x equal to 15. So the x value will be 15. It should be intersecting the line 8x plus 8y equal to 160. So I can substitute x equal to 15 in that equation. So I will get the second value to be 5. So 8 multiplied with 15 plus 8y equal to 160. If I solve that equation, 8y equal to 40. So that will give y equal to 5. So that is how I get 15, 5. So that is this corner point up here. Finally, this corner point is the intersection of the two lines, 8x plus 8y equal to 160 and 4x plus 12y equal to 180. So I can use the calculator to find the point of intersection. So we come up with 7.5 for x value and 12.5 for the y value. So these are the 5 corner points.